Thank you for inviting me to talk at this meeting. As I said, this is on Zoom and my screen is now in full screen, so please just open your mic and interrupt me if you have a question, as has just happened. So what I'm here this afternoon or morning, whatever you have it, to talk about is to learn about what do we learn from making jet measurements in p-gold collisions at RHIC and the LHC. Traditionally, we look at heavy iron, gold-gold, or lead-lead collisions to understand about the quark-Gluon plasma that we make when we collide a nuclei together. It gets hot and dense and makes a liberated state of matter. And then often, especially in the field of heavy ions, we collide PP collisions as our baseline. P-gold or P-lead sits somewhere in the middle, and that's what I'm going to talk about today. So before I do, I'm just going to move on and make sure we're all on the same page. I know you have a lot of talks about this later in the week, about what a jet is, what a hard process is. So hard processes have a large scale in the collision, meaning that they're calculatable directly by perturbative QCD. And what we mean by a hard process is that it's either a high momentum transfer, it's a high transverse momentum. The Q squared is what we call the high momentum transfer of the collision, or that the particle or parton created has a high mass. So of course, because of a high mass being the hard scale of it, so by high mass we mean making a charm or beauty quark or something even heavier, this can mean that they have a low PT and they're still a hard process because the Q squared of the collision goes into making the mass. So this is very early produced in the collision. So occasionally when a proton-proton or a p-gold collision happens, you have a parton-parton interaction with a large scattering as indicated over here. So the partons come in the beamline, you have a hard scattering and a parton comes out back to back in the transverse plane. As they come out, they make a stream of particles because you can't have a colored object, so you get this stream of particles. And because it's calculatable by perturbative QCD, we can calculate this in theory. It's a very well calibrated probe, or in PP, it's a very well calibrated probe in the vacuum. And so we can use this as a baseline because we know theoretically what it should look like, and we can compare it to our measurements at the colliders. So what is a jet? As I said, occasionally the two nucleons collide, and inside those nucleons, you have a hard scattering of two partons that come out back to back. But because QCD tells us about confinement, that colored objects can't exist on their own, this colored parton that's been knocked out of the proton or out of the nucleus has to come back on mass shell and become a colorless hadron. And what you see then is a stream of particles that hit the detector that are in a very collimated direction, and this is what we call our jet. So to a theorist, it's the parton that is cutting out and the energy that comes off the Q squared of the collision. To an experimentalist, it's a slightly different view. We have all the particles that come out of the collision, most are going down the beamline, and then we have these two back-to-back collimated cones of particles that we gather together to try and be that the sum of all the hadrons, if we could get all the hadrons that come out of the fragmentation pattern, they would add up to the energy of the parton. So we would know the energy of the initial collision. It's a multi-scale, complex, dynamic object, but it's calculatable from first principles in QCD. So that's sort of theoretically what a jet is. How we talk a common language between the experimentalists and the theorists is that we use what are called jet finding algorithms. The most common one that we use is called the anti-KT, which is a sequential clustering algorithm that essentially you can think of it as starting as the highest momentum object in the collision and then gathering particles around it based on a distance parameter that is a weight of the physical distance in eta phi space and the energy that it's there. The pro is, as you can see in this diagram here of running an anti-KT algorithm on a proton-proton collision, where we've unfolded it into phi and rapidity space, you get nice conical shaped jets, and the anti-KT algorithm is very background resistant. So especially in events with a large amount of pileup or in AA collisions where there's a large background, you get hopefully mostly the energy of the parton and very little of the rest of the event. The con is that we assume that the parton fragments from high to low momentum and makes these sort of spherical looking objects. So the resulting substructure isn't necessarily how the jet actually evolves in time as part of the fragmentation function. But a couple of the very important things that allow us to compare theory to experiment almost directly through these jet finding algorithms is that it's what we call infrared and collinear safe, meaning the soft backgrounds, very soft particles don't matter. They don't affect how the jet finding happens. And if you take one particle and split it into two that have half the momentum, so the total energy stays the same, it will still form the same jet particle. And that component of being IRC safe is essential for this comparison between experimental data and theoretical calculations. And this is large part why, at this point in time, the anti-KT algorithm is a common one that's used by almost all experiments and theory. So why should we study jets in PA? Well, there are a lot of interesting questions to ask, and it's also a very clean probe of QCD processes. The hard scattering scale is still well controlled. It's very close to what we think of as being the PP as opposed to the AA baseline. So it's very useful for studying cold nuclear matter effects over hot nuclear matter effects. And what we mean by that is the hot nuclear matter effects are the quark, how the jet interacts with the quark-Gluon plasma. This is a big field of study, and we're going to talk about that a lot later in the school, I understand. So we have these measurements that we make in AA. We have a PP collision, but we want to look at what happens if we have cold nuclear matter. So we put a nucleus into the collision, but we don't expect the quark-Gluon plasma to be formed. So this will help us prove that what we see in AA collisions and are currently attributing to being effects of passing through the hot, dense medium that we make this quark-Gluon plasma, that it's not just due to taking a proton and binding it into a nucleus, binding it into the gold or the lead. So that allows us to separate hot from cold nuclear matter. Another way of saying that is to separate initial from final state effects. The initial state being what happens when you bind the protons and neutrons into a nucleus, the final state being what happens as it interacts with the quark-Gluon plasma. And these cold nuclear matter effects, there might be some. Can you see the effects of the parton coming through the rest of the nucleus after the collision? Do we see some initial state energy loss trying to pass through the other protons and neutrons that are there in the cold nuclear matter? And it also tells us something, again, we know, and we're going to explore further in this talk, that when you put a proton into a nucleus, that you affect the underlying nuclear parton distributions. It allows us to look into these effects, the effects of shadowing and anti-shadowing of the rest of the nucleus being there. And I'm going to come back to that in a bit more detail about what a nuclear PDF is. And it helps us test factorization, whether this holds when you put a nucleus in there and the structure that it has. And again, we're going to come into more detail about what that means. And last but not least, it helps us probe for effects of gluon saturation. So let's start off with separating the initial versus final state effects. So first, if we're going to separate hot from cold nuclear matter effects, let me quickly show you what a cold nuclear matter effect is and how we measure it when it comes to jets. And it largely comes down to the nuclear modification factor, or RAA or RCP, you'll see central to peripheral collisions. And what this is the yield of jets in a heavy ion collision, in an AA collision, compared to the yield that you would expect in proton-proton, scaled by this N-col, the average number of PP-like collisions one would get in an AA collision. So if you collide lead on lead, you expect more than one proton or neutron to collide with more than one proton or neutron in the other collision. So we scale that up. And if nothing happens in a heavy ion collision, except for it's a very complicated way to make multiple PP collisions in one go, then we would expect this ratio, because it would be the yield in PP times N-col divided by the yield in PP times N-col, we would expect this ratio to be 1. The RAA to be 1 is no effect, it's just a superposition of PP collisions. If the RAA goes to less than 1, then we know that something has happened, that there's been an energy loss, that we start off, because the initial hard scatterings are made at the very start of the collision, before we have a quark-Gluon plasma formed, So you have the same number of binary collisions as goes into our assumption for the nuclear modification factor, but they lose energy, so the spectrum essentially moves to the left on the plot, and then when you take the ratio, you would have something less than 1. So we expect an RAA of less than 1 if we have interactions of our partons with the quark-gluon plasma. And that here that you see is, in fact, there's a very strong suppression. Here you see sort of a combination of the results from the LHC in their central lead-lead collisions, so their most overlapping collisions. And as you can see, the hadrons, so there's lots of them here, pi, kp, basically all particles, charged particles that we make that are formed out of quarks and gluons, are very heavily suppressed, even up to 100 GeV. The ratio is about a factor of 2 to 5 smaller than you would expect from a PP superposition. But then that question is this very trivial scaling that I mentioned about just scaling by this n-col, the number of expected PP-like collisions, actually true, or do we just have that number wrong? And that's what you see by these here. So this blue, this pink, and then large error bars at this point, the gold. But if you have colorless objects, so the orange color here is photons, they're colorless, they're not made up of quarks and gluons, or you take the W or the Z, that the RAA that we measure is equal to 1. So we have this unitary scaling when we have an object that doesn't interact with the colored objects. So we have a clear indication that there's something about coming from a colored object that makes there be this enormous suppression when you have an AA-like collision. The colored objects suffer energy loss, but now we need to know, is it initial or final state? That's our big question. And that's where the cold QCD baseline of P-lead comes in. And so I have a variety of nuclear modification factors, all from the LHC in comparison, again for charged particles. And you see that for the pi 0, the ratio is very nicely at 1. So it is here for full jets out to 2,300 GeV. Again, you see it here within uncertainties, the ratio sits at 1 for the jet, pushing it out with better statistics. And if I change even a little bit the rapidity range, you still see this ratio at 1. So the suppression in AA really is due to final state effects. And this was one of the key results that came out of colliding. PA, I've shown you here only the results from the LHC, but we have very similar results that come out of the RHIC as well. So we can see that its final state effects, there's very little effect from the cold QCD. It's a final state effect in AA. So having said our cold QCD baseline is doing what we expect, then let's get back to talking about this nuclear PDF that I mentioned. What happens, or does anything happen? It appears from what I just showed you that my talk is over and nothing exciting is happening in PA collisions. But we want to look into this idea of a nuclear PDF. And what is a PDF anyway? This all comes down to what I mentioned about the factorization that we understand happens for our calculations of hard processes. So this is a bit of a busy slide, so let me walk you through it. What it's showing you is the cross-section, which is the probability that a hard scattering happens, that PP collision turns into producing the hadron, the jet, whatever type of collision you have, is built up of the sum of the parton distributions, where the parton distribution, or the PDF, is the probability to find a parton A with a momentum fraction x in a hard collision scale of q squared inside of a proton. So because it's a proton collision, you have the probability of parton A finding parton B. Then you have the probability here, the parton scattering matrix element that tells you what's the probability of that collision happening, that you have A, B turn into C. And then you have the probability that parton C fragments via the fragmentation function into a hadron H that carries a certain amount of Z of the collision. So we have the parton distribution. This is not measurable experimentally. It's only measurable experimentally. It's not calculatable by PQCD. The parton scattering matrix is the only part of this equation that actually is calculatable by perturbative QCD. And then you have the fragmentation functions. And both the green and the blue term have to be measured by experiments. The fragmentation functions we can measure because it says if I have parton C, how does it fragment? that we can measure via jets. And it's this parton distribution that is what we need to probe into. What is the probability that you find a parton with a momentum fraction x of the proton given a resolution scale of your probe of Q? As I said, it's not calculatable, but here you see we can determine them by using global fits to the experimental data via deep inelastic scattering of electrons, looking at the Drell-Yan cross-sections, looking at the jet cross-sections. And if you take many different experimental data, you can do what's called this global fit, and you can extract the parton distribution for each of the different partons. So you see at about a third of the X, the up and the down quarks, it's highly probable if you look around a third of the X that you find the constituent quarks of the proton or neutron. And then you see that we have the anti-C quarks, you have the SS bar, very rarely do you manage to get charm. And then note, please, this gluon scale that is actually divided by a factor of 10. As you go down to very low X, it's more and more probable that you find a gluon. The gluon density gets very extreme. And you see that the parton distributions look quite different depending at what scale you probe it at. If you look at a scale of 10 GeV or 10 to the 4 GeV, you see that they look very different. So we need to be able to evolve as a function of Q squared. And how we do that is you determine from an experiment at a scale of, let's say, 10 GeV, what your parton distribution looks like. You parameterize it at this fixed scale of Q0, and we know via equations how to evolve this to any other Q that we have. And the higher the Q squared that we probe, we manage to make of the collision, the deeper into the proton that we probe. So that's what the parton distribution in PP looks like. A lot of this work has been done by looking into EP collisions. But then we want to place the proton and neutron inside the nucleus. And that, therefore, we see that, again, we've got these arguments that I was talking about. If you put the proton into the nucleus, does it just behave like a superposition of PP? And we saw from the Quark-Gluon Plasma measurements that the interactions are different when you put the Quark-Gluon Plasma there. But even if I don't, the nuclei is not just a simple collection of free protons and neutrons. The cross-sections don't scale with just the number of nucleons in the nucleus. There's something different happening. And this first was discovered by the European muon collaboration via DIS, and they showed that this scaling doesn't. And so we see here we have the equivalent measurement of probing something at a certain X of the collision, the momentum fraction inside the proton. If you take the measurement in PA or EA, and then you divide it by what you'd expect when there's only a proton there, you get this ratio. And you see, as a function of X, so going down, this would be that it's taken all the proton momentum. This is getting a smaller and smaller scale. You go through these different regimes. So there's a so-called EMC effect, due in part to the Fermi motion. It's called the EMC effect because of the collaboration that discovered it. They noticed the structure functions were different. As you go down to lower one, you get to an anti-shadowing, so you see an enhancement of what happens by putting the proton and neutron into the nucleus. And as you get down to this lower and lower X, looking more and more at the gluon contribution, you see a shadowing effect, that putting the proton in the nucleus causes us to not see as well, or less effect of putting it in the so-called shadowing region. So we expect to see differences. So we have to measure these nuclear PDFs if we're going to try and understand and determine, for example, what the cross-section theoretically is of a jet in an AA collision. It's a universal scale. It's been shown now across many nuclei and experiments that this pattern of going through a suppression at very high X, then you see the anti-shadowing, and then you see the shadowing, is a universal of nuclei. There's not a different one for every single nucleus that you have in there. So back to nuclear modification factors. Now we're looking at the nuclear modification factors, putting in the numerator the PA, in this case, the P-lead collision. And you see, as a function of rapidity, so each of these plots is going from backwards in the lead going direction, coming forwards towards mid-rapidity, and then going into the proton going direction. And you see that the ratio is largely within uncertainties, consistent with unity, and the data in the black and yellow compared to the theory that includes, importantly, a nuclear PDF is in common agreement with it. They're consistent with those, including nuclear PDF effects, where the nuclear PDF was determined from something other than a p-lead collision. But we have a nice working together here, showing that the evolution works. And the reason why we're breaking out these rapidities is it allows us to probe different X regions. However, if you're looking at the inclusive jet cross-section, that's what we're doing here. Note the scale here of the transverse momentum goes up to about 500 GeV. We're integrating and probing over an X range via these different X's that ranges from about 0.02 to 1. So what about, like, as I come out, I said the other thing we want to look at is there energy loss of passing the parton coming out and trying to get its way through the rest of the nucleus before it emerges and can fragment in the vacuum. And what we're looking at here, again, in p-lead collisions from the LHC, we have higher energy jets. We allow the subleading jet, the back-to-back one, to be a low momentum in case there is energy loss. And what we compare is the momentum of the subleading divided by the momentum of the leading. If there is no energy loss, and that's what we see here, you see sort of the baseline sitting a little bit lower because it is a subleading, so we're biasing the subleading to always be lower than the leading, and that's just resolution effects of the jet cone angle that we're looking at. But you see it's very consistent between here in lead-lead, these yellow points, and what's expectation is from PP. So we expect the ratio to be about 0.7 rather than the very naive value of 1, because it would be 1 if I could measure the leading parton to the back-to-back parton. But because I run this jet finder, remember I mentioned there was a distance parameter that we look at, so we don't necessarily gather in all the energy into the collision. But there is no significant reduction, it's much less than 2% of energy loss as we pass through cold nuclear matter effects. So again, we're showing that the jet quenching that we see in AA collisions has got nothing to do with cold nuclear matter effects. It's not due to the nuclear PDF. It's not due to energy loss of the scattering as it tries to break out from the through the lead nucleus. It's not an initial state effect. Again, one more time, we're showing this is not an initial state effect that we're measuring in AA. But what about the substructure? Maybe it still matters that it's in there and we have some variation of how the fragmentation happens if it starts to maybe fragment as it's still within the lead nucleus. But here you see again, there's no significant cold nuclear matter effects. We're looking again at the nuclear modification factor of jets with going from reasonably low momentum jets, increasing in energy left to right, and then the bottom row is up to 250 GeV. And you see that the ratio as a function of the Z of the hadron, so we're now really looking at the substructure of the jet, still sits around 1. There's no nuclear modification factor due to cold nuclear matter effects. I promise you I'm going to stop saying that in a second. And then we look at here at Alice, again, you're looking at a different form of a fragmentation function. But once again, this ratio of P-lead to PP over the whole range of what we're looking at, this is the transverse momentum of the particle within the jet. There's no modification. There are no significant cold nuclear matter effects or final state effects when you look at PA collisions on either the number of jets, the energy of the jet produced, or even how the fragmentation of that jet occurs. So, but we want to go a bit deeper into this because I told you the X is important. And when we take inclusive jet measurements, we're kind of integrating over a large range in X. It's very hard to tell what X are we actually looking at. So this is where dijets come in, really measuring the back-to-back, the pair of them. And then if you look at the dijet pair rapidity, which is the average of the jet of the leading and sub-leading jet, you can show, after a bit of consideration of how sort of rapidities are defined, that this is proportional to the X of the proton that you are probing with some center of mass shift, but that's just a shift. So you can calculate this dijet pair rapidity theoretically. It can be calculated via perturbative QCD. We're talking about X factors. These are rigorously calculatable in PQCD. And experimentally, what's nice is by measuring a jet experimental property, we can probe into the perturbative, the partonic degrees of freedom, avoiding this complicated fragmentation and hadronization effect. Because I told you, when we're trying to calculate the BioPQCD, this is another part that we assert has to be separatable out because we can only measure that experimentally. And by looking into this dye-jet rapidity pair variable, we get rid of the complications of that one. And by looking at the average PT of the back-to-back jet, in principle, it should be the same because it's coming out of the hard collision. We have access to the Q squared of the collision. So you see, I'm nicely getting access to things I was looking at in the nuclear PDF, both the Q squared and the X of the collision. And here you see this is a simulation as a different jet PT averages, the different color lines here. If I look at different eta jet defined here, the dye-jet pair, I am probing different regions. I'm probing if I go to negative eta dye-jets, I'm looking into the shadowing region that I expect of the nuclear PDFs. If I go to mid-rapidity, I'm looking at anti-shadowing. And if I go to forwards, I'm looking at the EMC effect. So I'm now digging out those different ratios that I was getting because of the nuclear PDFs. I can really start to probe nicely how these affects the jet kinematics and the parton kinematics. And that's what you see here. So here I'm looking at the dye-jet eta on the x-axis, and I'm moving through different PT averages as I move through the plots. And then because I'm plotting it at different eta jets and different PT, I'm digging out as a function of these variables, the different effects of here, the anti-shadowing effect. You see that there's a slightly increase in the ratio as we would expect from the anti-shadowing. Remember that graph from earlier. If I go to the positive eta regions at higher PT, I start to see the effects of shadowing. I see the suppression. And again, if I go to the negative eta dye-jet regions, I'm probing the EMC effect and I see this impressive suppression. So I have very good agreement between the data and that the data's in red, the theory curves that include these NPDFs are in there, and you see this nice agreement, and I'm really teasing out these different X regions, these different effects, and understanding how to use it. And there's good agreement already between data and theory, but with all the data that is now coming out of the LHC, we're really minimizing also the uncertainties as we fold in these data now into recalculating what an NPDF looks like. You see that the uncertainties that we have here, which are rather large, notice the green uncertainties are bigger than the data. These are getting better and better and more known. So with nuclear PDFs, as long as we include these, we're beginning to understand or at least be able to tease out the different X regions and how that is. We show that factorization still works even in PA collision, as long as we replace the PDFs measured for PP collision with nuclear PDFs. And we've shown from the variety of data, I was showing you mostly the LHC data, we've also teased some of this out at RHIC, there's a consistency across systems and energies. So it doesn't matter what nucleus you collide, and it doesn't matter what square root S you collide. As long as you can tease out what Q squared and X you're at, the nuclear PDFs are the same across it. They describe data from fixed target experiments at low square root S up to the collider energies at the LHC, as I was showing you. We've teased out the A dependence of it. We know what those look like. And we can predict new observables. So we don't just fit what we have because you think, well, if I fit the data, of course I can then explain the data and it's a fitting exercise. But you can really predict new observables that are not used in the measurements that constrain the nuclear PDFs. But it all seems quite simple, all right? So now we've managed to explain the cold nuclear matter effects are not important in AA, that the nuclear PDFs, that factorization seems to work. So what am I going to talk about for the next sort of 20 minutes or so? Well, then we started to get smart and our controls started to go a little bit out of control. So we decided to look at P-led events instead of the inclusively, to look at them as a function of multiplicity of how many particles were actually created in the collision. And if you look at the inclusive, what you see here is a function of delta eta now, not eta, but delta eta, the separation in rapidity between pairs of particles. And in delta phi, you see this well explained on the average one in PP collisions at very small delta eta, so close to 0, and also delta phi. You see this collection of particles. This is the jet fragmenting on one side. And then you see the jet on the other side at large delta phi, so basically pi, but it's smeared out over delta eta because this is built up over many events. And whilst the jets are back to back in the transverse plane, because of the motion along the beam axis, they're not back to back in either. So you've got lots of these little jet peaks sort of summing all the way up across it. So we understand what this plot of the correlation in delta eta, delta phi looks like in PP collisions. And it looks fine when you take small multiplicity events in P-LED or the inclusive, but when you take the very extreme P-LED events, and so very high when lots of other particles, not just the dijets, but many other, the underlying event, you start to see this very distinctive ridge that's coming out of here. It gets more and more detail. And when you project now just this region onto the delta phi plane, you see this very distinct oscillation of a cos2 phi that's being used in AA to attribute it to collective flow, meaning that there's a collective motion, the fluid-like motion with it, defined from the ellipticity of the event. So now we had evidence of what we thought was one of our big signatures of the Quark-Gluon Plasma in AA, turning up in P-LED collisions. This was happening in sort of the early 2010s, and confusion started to reign because our cold nuclear matter baseline, where there wasn't supposed to be a Quark-Gluon Plasma, suddenly has flow-like signals indicative of a liquid of partonic degrees of freedom. We managed to tease out more. You see here the elliptic flow as a function of transverse momentum for many different particles. You're going to hear more about this, I'm sure, from somebody. This splitting of the particles into baryons and mesons, again, was being used as indicative of there being a quark-gluon plasma. So maybe our cold nuclear matter baseline in P-LED was maybe not such a cold nuclear matter in state at all. And we see similar ones at RHIC. There's indications that there's a fluid. So we went back and we were trying to tease out from our PA collisions, because remember I said there was no signs of jet quenching in our PA collisions, and that still seems to be true. Here's something equivalent to the RAA. It's called the IAA. It's the per jet charged particle yield. So you sum up the sum of the particles, how many there is in a jet, compare that in P-LED and PP, and you see that there's this slight enhancement because we're mostly in the anti-shadowing regime, but it fits with cold nuclear matter. So we have some soft bulk measurements that seem to be declaring that there's a quark-gluon plasma, but no clear signs of jet quenching. So maybe we would just make a very small quark-gluon plasma in the more central PA. It's small, but it is a liquid drop, so you start to see collective motion, but it's not big enough or long enough lived to actually cause jet quenching, to cause energy loss of the partons passing through it. So the test was thought up. Here you see the sort of theoretical idea behind it by our collaborators at RHIC on the Phoenix experiment. They said, well, if you have them in these extreme, if I collide P gold versus D gold versus helium-3 gold, I should see differences in this elliptic flow. Because if a P hits a gold, there's no real ellipticity, so you wouldn't expect to see much of a V2 signal because the P is very small but spherical. If I take D gold, so I combine two nucleons together, there's a chance that it becomes very elliptical, so I should see an enormous V2 in D gold collisions. And if I take helium-3, it has more of a triangular, so I should see a large V3, how triangular it is, but I should also have a V2 because you can see I can draw something of an ellipse through this. So that was the proposal. We could collide P gold, D gold, and helium-3 gold and see if this very simple fluid-like behavior due to the initial conditions, the initial overlap region, would be borne out. And here you see the results that came out, and it came out amazingly like was predicted. So in red, you see the P gold, very small, hardly any V2, much smaller than in the D gold and the P gold. Whereas if I look at the triangular shape, you have a much larger here in black helium-3 gold signal and a much smaller p gold and d gold. So we seem to have, here you see it, the plot sort of on the right, put back onto the left, and compared to calculations that assume there is a hydrodynamical system, and there's beautiful agreement between the data. So indeed, we are making in these extreme, and I want to remind you, this is the very extreme, very highest multiplicity events that are made in each of these collisions. We have a system that is flowing just like a fluid, just as we have in AA collisions. But we didn't see any obvious signs of jet quenching. And people have gone in and looked since to sort of say, well, maybe it's not there as a big energy loss, but you still see an effect on the fragmentation, but it's sort of, the modification is sufficiently small that our jet finding algorithms still find all the energy, but you modify the fragmentation. So tests were done by STAR in the P gold, measuring the substructure via the jet mass. And here you see it in P gold versus PP. So black is the PP measurement and blue is the P gold. And the reason you can't see the black very well is that it's almost perfectly on top of each other for different jet energies. When you look at the very peripheral event activity, the low event activity, where we were saying there wasn't any PA, any obvious flow signals either. But now when you go up to the higher momentum ones, it's the same plot, but now we're comparing the low multiplicity P gold to the high multiplicity P gold in red, and you see again that the ratio is 1. So there's no substructure differences. Not only is the RAA equal to 1 in these PA collisions, but you also see no substructure difference. And similar conclusions have come out of the LHC too. But then, we keep looking, we keep probing deeper and deeper. The LHC started exploring what the jet central to peripheral data looked like in these P-led collisions, not only as a function of the event activity, but also as a function of the jet PT and the jet pair rapidity, the rapidity distribution. So the blue in these curves are the lowest event activity, red is the mid-event activity, and black is the highest event activity. And you see it in different rapidities going from positive rapidity to negative rapidity as I work my way through the data. And now you see an even more confusing signal coming through, having just decided, well, maybe in the most extreme PA collisions, I make a little droplet of quark-gluon plasma, but not enough to make any modifications to the jets. Here you start to see enormous modifications, especially at these proton-going directions. You see a big suppression here in black of the highest event activity, but more confusingly, you see an enhancement in the lowest event activity. So we could understand maybe the suppression as being due to jet energy loss as it passes through this tiny quark-gluon plasma droplet. We would understand it being at unity because that means there's no interaction or very little modification. But how do we get an enhancement? And apparently whether you get an enhancement or a suppression depends on whether I'm looking at positive rapidity or whether I'm looking at negative rapidity. So the interpretation, again, was initially unclear. There was lots of discussions, as you can imagine, at conferences about these results from Atlas. But then Atlas thought, well, let's have a look. X is normally important for what happens when you make jet collisions, when jets are produced in the cross-section. So instead of plotting on the x-axis the jet momentum, what we plot is something that approaches to the x that you are probing in the proton. So you take the square root s, you take the average pt, and you take the rapidity. So you can transfer your jet measurement into what x you were probing. Here we're using dijets, and so I can tease that out. Remember I told you from the dijet pair rapidity, you can start to tease out the x. This is what they're doing. And now you see there's a very nice correlation between the x that you are probing in the proton and how much suppression there is. So it's essentially the same data you were just seeing. I'm just changing what I plot on the x-axis. And there's a very nice linear correlation when I look in the x region of probing the protons, in the proton going direction. At small x, there's no suppression. At large x, there's very high suppression. So it's not a final state effect because it depends on the X. It must be an initial state effect. And how we now understand this is that when you look at the large X of the proton, remember X is a measure of the fraction of the momentum the parton has taken from the proton. If it's large, look, we're getting very close to 1. This is a very rare configuration. It means one of the quarks in the proton or neutron is essentially carrying all the momentum of the proton. Now, if it's carrying all the momentum of the proton, there's not a lot of energy left to make other particles in the event, to make the soft background over all of them. And so the event is classified as a low event activity event, and the high XP jets are therefore biased against happening in high energy collision, what we call the central. And so when you have high X, you're more likely to have them in low event activity, that's the denominator, than you are in high event activity. So you see this apparently large suppression. But it's due to energy conservation of the partons, or the other way people think about it, about the size of the proton fluctuating. Because if one parton is taking essentially all the momentum of the proton, you can think of the proton as being very, very small, and so less of the interaction happens. So we're beginning to understand and put it into being looking in the proton going direction at the X of the proton. And as I said, we will attribute this to not being a final state. And one of the last ways we sort of think that we've proven this is if I take the same type of data, but instead of looking at the positive rapidity, I look at the negative rapidity. So look in the lead going direction. That's what you see as this plot here, the same scaling, just looking at the rapidity when the rapidity is in the lead going direction. You don't see this scaling comes out. There's still a strong dependence on what rapidity you're looking at. And that would not be true if it was a nuclear PDF effect that was causing this suppression, or if we were getting to signs of gluon saturation that I'm about to get to. This would all scale with the lead X that you were doing it. How deep inside the lead nucleus are you probing? And it's not. So these suppressions are understood as probing the parton X distribution. But what about at RHIC? Do we see a consistent picture? That was LHC results. And indeed we do. And here you see a similar idea from STAR, where they're showing a clear anti-correlation of a high jet PT with the forward event activity. It's a little bit of a complex plot to first pass, so let me walk you through it. So in colors, let's focus on the orange is a very low jet momentum, and in red is a high jet momentum. And what we're on the x-axis, the y-axis is the probability that you see such a jet in the event as a function on the x-axis of the BBC signal. This is just a way of saying essentially how many particles are produced in the very high forward region, away from where the jet is. The jet is measured at mid-rapidity. The forward activity is measured a long way, so there is no jets. It's really what is produced in the underlying event. And when you have a small underlying event, you are more likely to have a high momentum jet. And when you have a high event activity event, you are more likely to have a high jet momentum. Back to this idea of looking into the X of the proton, if the one of the partons takes away a large fraction of that momentum, you're unlikely to have a large event correlation. So the same picture at RHIC as what was deduced much more clearly because of their beautiful statistics at the LHC was seen. We were just beginning to get back to our cold nuclear matter system is under control when Phoenix showed this beautiful analysis, which still has us scratching our heads. So what they're showing here is the RAA again, the central to peripheral ratio, but instead of determining the number of binary collisions, the number of a scaling of how many PP-like collisions was there, using a Glauber calculation, using theory, they did this via experimentally, because remember right at the beginning, I showed you that colorless objects scale with the number of binary collisions. So they forced the RD gold that they were measuring of their photons to be unity. They figured out what do I have to scale the PP by to match the D gold results. And that's the number of this N experimental collisions that they do. And then they use that number to work out what the RAA would be for the pi zeros where it's a colorless object. When you have a peripheral collision, you see we're back at unity. But when they go to these very extreme 18 collisions in a D gold collision is a lot, you see a very strong suppression of the pi zero in high multiplicity events. This seems to be at odds. This is not the same explanation as STAR and the LHC have, because they've taken out, instead they've worked out how many binary collisions were there actually in the event. So they get rid of this bias of the event activity selecting it, anti-it against you, and they see this very strong suppression. And we're still struggling to understand this. Maybe indeed they have found a way to tease out this energy loss due to the little droplets of Quark-Gluon plasma that we see. That's for the proposal that's there when you go to very extreme events. You see it's only a ratio, it's like 20%. It's not as much energy loss as we see in AA collisions, but maybe there's a sign of actually this Quark-Gluon plasma is causing energy loss in the most extreme PA-DA type collisions. But the discussions are still ongoing. So I mentioned our last point that we get to, and I'm nearing the end of my talk here, is looking into the gluon saturation. So first of all, what is gluon saturation? And that gets us back to these nuclear PDFs and PDFs. And as I pointed you and told and highlighted, you have the valence quarks sort of at that intermediate X, about a 0.3, about a third. But if I look at the gluons, if I go down to very low X, the probability that you find the gluon there, it gets more and more extreme, especially at the higher Q squared, because note again that this is divided by 10, and it just seems to keep on growing and growing and growing. But we know you can't have an infinite number of gluons, so at some point the gluon density must saturate, and that's what we think of as gluon saturation. At what X do you have to probe down to such that this probability plateaus off, that there's so many gluons that you can't get anymore, you have a saturation of the gluon density. Experimentally, we get down to low X by either going to low PT at high square root S, or by going forwards, by going to higher rapidities. Theoretically, frameworks such as the color glass condensate, the CGC, you might have heard people talking about this, is how we try and explain the effects of saturation. So we believe there is saturation. What should we see? What are the experimental signatures? Well, there'll be multiple scatterings of this dense gluon field. Because you're sort of hit this saturation, there's an enormous amount, basically a field of dense gluons there. So there should be a smearing of the transverse momentum as you have these interactions or multiple interactions that are going on. So if I look at dijet correlations, I should see that the back-to-back correlation are broadened and maybe even suppressed if so much scattering goes on that you just lose one of the dijet partners. We should see that the saturation scale, so when do we reach that at the Q squared to be able to resolve the saturation, goes as the stronger effects for heavier nuclei, this is the A of the nucleus, and should be stronger effects at lower X. Notice the minus sign here. And this lambda parameter is expected to be around 0.2, 0.3, something less than 1. And we should also see that when we reach the saturation region, there's a flattening of the gluon density because it's saturated. And so because particle production scales with the gluon density, you should see that the cross-section as different X's starts to plateau also. For jets, it's complicated to look at it. There's a lot of interplay of other different effects going on. But if I look at heavy quark production, that should scale with the gluon density. Or one of the most popular ways to look at it is to look at the vector mesons, sort of the ones that have a JP1 minus, that one should expect them to stay with a square. So you have a lot of sensitivity if you can look at vector mesons. But there is no unique signal. So these are all what one would expect to see from gluon saturation, but there are usually other effects that might be able to explain this. But still, we want to go and have a look, and there is mounting evidence for gluon saturation that we are starting to get into those regions. So the first evidence, or strong evidence, came from RHIC by studying pi zero. So we're not looking at jets really, we're looking at the leading particle of the jet, high energy pi zeros in the forward-backward regions in PP, P aluminium, and P gold. Because here, remember, we have the A to the 1/3 dependence that we see. And so we see the effect. So here you see what the delta phi distributions look like for, in blue is PP, in black is P aluminium, and in red is P gold. Here you see them subtracted from the baseline. So we don't see any broadening of the correlation. Note they sort of lie on top of each other once you arbitrarily scale them on top of each other. But there is a clear suppression, right? You see, as we go from PP to P aluminium to P gold, the yield is actually getting smaller. If you integrate up the area of these curves, you see a beautiful correlation that goes as A to the 1/3. So we have the first bit of very strong evidence that when you go to small x, because these are at forward rapidities, remember that gets me to low x, and at q squareds that are reasonable, that you see a hint of the A to the 1/3 dependence, nonlinear gluon dynamics are at rise here. Evidence of gluon saturation. And not from jets, because like I said, that's complicated to tease out, but just to sort of show you that we're also starting to see these at the LHC. So we look at the J-psi via photo production to get a clean signal. This is ultra-peripheral collisions, where the fields of the nuclei are interacting. So although it's a lead-lead collision, you're not making the quark-gluon plasma. And if you look at this, if you look at the W, so the photon-nucleon center of mass, because we're having this interaction of a photon with an A, it's an asymmetric collision, you can think of it. But if you have a photon-A interaction where the photon field of one of the lead nuclei interacts with the actual lead nuclei and produces a J-psi plus some other stuff, we can look at the probe of this as different square root s's, and we go down to an x of 10 to the minus 5, and you see the sharp rise. But as we get to higher and higher square root s, and remember higher square root s, because you divide by it, gets you to smaller and smaller x, you see a plateauing of the yield of the J psi as a function of this W. The shape is not predicted particularly well by QCD models, and the saturation of the cross section, the plateauing of the yield, the probability that you make a J psi, is again some evidence that we're reaching the gluon saturation reach. But as I said, for both of them, it's not the only way you can do it. Here you could also just be reaching what's called the so-called black disk limit, that the probability that you see have an interaction just starts to raise. There's so many gluons there that the probability of an interaction just basically reaches 1, but it's not because you have saturated the gluon density, you just have a very high one. But there's two very strong teasers for both RHIC and the LHC that we're starting to get down into the gluon saturation regime. Where we're really hoping to do this is in the studies of the EIC, the electron-ion collider that's about just begun construction at RHIC. RHIC shut down last month, as I'm sure many of you are aware. There's no more collisions coming, though a lot of data analysis to be done, to build an electron-ion collider. And why you want the electron is that you can do EP and EA collisions at very high luminosity over a large range of center of mass energies and with a large range of ion species. So that A term that I was telling you about and we've been talking about repeatedly through this talk will be doing it. And we can probe a very unique, you see here, this is with the range from here at the EIC to here in the XQ squared space for both EP and EA collisions. The dark gray and this funny orange is the regions that have been probed by current experiments. So you see, we're going to really be covering a beautiful range in Q squared and X, and we should really be able to tease out the the gluon saturation effects. How does a proton and nucleon look? So here I am at my summary. Why we study jets in PA, I hope that's now clear. There's a lot of very exciting things that come out of it that you cannot probe in AA or PP. We're separating out, teasing apart the initial state effects from the final state effects. And we need to understand the initial state effects if we're really going to understand completely what happens in AA and the QGP signals. We see that jets, the probes that we've been talking about, are not significantly modified by, this should be nuclear, by cold nuclear matter effects. Factorization works still, just as it does in PP, as long as you include the nuclear PDF, and the data that are coming from the LHC and RHIC are making these nuclear PDFs more and more understandable. And we've got small hints of the gluon density really becoming high and possible saturation that we hope are going to be revealed more and more by the EIC. The data on the EIC should turn these hints into very strong evidence. That's the goal, or one of the key goals of the electron-ion collider. But we also see, and that's where there's still a lot of interest, there's lots of data there for you all to be looking at, is that when you look at the high event activity in small systems, we do see unexpected collective behavior, but without JED modification. And the belief is that the understanding is that this is evidence of a mini QGP being created, but we're still not firmly sure about that. So there's lots more still to be done. And with that, I say thank you and ask for questions.
Thank you, Helen, for this insightful talk. And I hope our student and postdoc and also myself and others must have enjoyed and get into it. But now it's open for the question. Please raise your hand. Then I will go one by one. Yeah, Gaurav, can you just on your mic and speak up?
Yeah, nice talk. Uh, so I have a questions regarding the cold nuclear matter effect as you told. So the thing is, when you one of the slides you saw that the jet modifications only taking the cold nuclear matter effects, and I mean when you calculate the cold nuclear, yeah.
Getting back to it. Yep, keep going. Yep.
Yeah. So when you calculate the cold nuclear matter effects only, so have you considered the initial state? I mean the parton energy loss in this effect or not, or only taking the modifications only?
I believe most of these calculations just include including the nuclear PDF. They don't assert that there's any cold nuclear matter energy loss. It's not necessary.
Oh, yes. I mean, for the jets, I think it would be a nice feature because for the higher momentum, the energy loss is not so important initial state. But yeah, I mean, the initial state energy loss or the initial parton energy loss also, I mean, is a mm, what I can
You
say
see,
is a dominant effect in the case of Quark-Gluon sector. I mean, we are studying also this same things in the Quark-Gluon sectors. So, and we observe there the energy loss of the initial state has a significant impact. I think maybe for the jet that is less, but yeah, I mean.
right. So referring to the quark-gluon, the quark-gluon plasma, to looking at the J psi or the different quarkonia, is that what you're
Yeah, yeah.
referring to? Yes, indeed. So there they seem to see some more effective cold nuclear matter. And I think that's because of how of our current understanding of how quarkonia are formed and the fact that you now have to make a CC bar or a BB bar. And so indeed, they can tease out these tiny bits because you can see here, I don't have a lot of energy loss from looking at one parton coming out, but maybe there's room for some because, and also I think the effects, if I know rightly, I'm not a big quarkonia expert, but I think like this is stronger when one looks in the forward and backward regions, when you're really making the CC bar pass through the sort of spectator part of the nucleus. Whereas these are more focused at mid rapidity, where the spectator part of the non-interacting nucleus is going down the beam pipe. So I think that's part of the difference between what you're thinking of for these suppressions of the J psi or the other quarkonia compared to what's being shown here for the digets.
Yeah, exactly. So nice. Thank you.
Welcome.
Yeah. So I see Soham.
Hello. So in one of your slides, you had like the different ranges of PT of the jets, and like it seemed to that higher PT jets are the number of higher PT jets are higher. Uh, should that be the case? Because right, so the probability of having high PT jets should be lower, right?
I mean,
Before
let
in
me see if I get to the one that you're talking about. This plot?
No, before. So you take some range, just a PPPT of jets, and you
I'm still not sure which slide you're talking. So if I go slowly through, do you want to tell me when to stop?
yeah, sure. It's a bit earlier.
Getting towards. Those are my jet plots.
So you had okay, we can discuss later. I guess I missed the slide number.
Keep going. I'm happy to go through. So it's a jet distribution as a function of rapidity. Is that what you said?
No, it's a function of some complicated thing. So you have two plots on the left and right, and for different peak, like you chose some PT ranges of the jets. Okay.
This one. No.
I think this one. Yeah. So back.
This one.
Yeah, this one. Yeah. So why is like orange range lower than the red one?
Because when I have a low momentum jet, I have a lot of I only have a low X, so I don't take a lot of energy out of the proton very naively. So there's a lot of energy left for there to be a high event activity. So I guess the point is this is normalized. So it's not that there's less, it's just that there's a larger fraction out here at the high event activity, because the area of all these curves basically sums to 1. So if I have an increased probability of having a low momentum jet with a high event activity, then I must have a smaller one here. Does that make sense?
Okay.
All of these curves are 1. So it's not actually it's the probability as opposed to how often it happens. You do have more jets.
Lower PT jets. Yeah. Okay. Thanks.
Just the normalization to say, if I have a high event activity, so lots of soft particles created, I don't have a lot of energy left to make the high momentum one. So you see the biasing of the system. To make a high energy jet, I must have a low event activity because there's nothing left to make the event activity with. Is the argumentation.
Okay, thank you.
Yeah, Arc next. Arc, can you speak up? Really, you are muted.
Hello, am I audible?
Yes, you are now.
Yes, my question was on this slide only. Can you explain the how the anti-correlation is clear in high PT? I didn't get it.
So if you have, so this is the event activity. So higher numbers are higher event activity. That's what you can think of it like. It's not quite correlated because of the numbers to, I mean, it's not directly the number of particles, but it's correlated with. If I have a high event activity event, I am more likely to have low momentum jet produced. So the gold color is above the red color, because if I take the energy out to make the event activity, I don't have enough left to make a high energy jet, and vice versa on the other side, that if I make a high energy jet, I don't have a lot of energy left to make the bulk particles, so I have a bias towards it occurring in low event activity events. So low event activity, not many bulk particles, I have a high jet energy because the X that's taking away all the energy of the proton. If I have a small X collision, small Q squared collision, so I don't take a lot of energy out of the proton, then I have a lot left to make the bulk particles, and so I have a high event activity.
Okay, thank you. Got it.
Yeah. Sayantan.
Hi, Helen. Thanks for this fascinating talk. So I had one naive question. So in the LHC, you showed is it possible to measure events as a function of the rapidity?
Yes, so that's what's
Differential
happening.
rapidity. Okay.
This is what's happening here.
So
So this is the
yeah, sorry, go ahead.
So this is what's happening here. So they're measuring the RCP. So we talk about central to peripheral. In PA collisions, it's not clear that the centrality is the same as the geometry in AA, but central basically means high event activity, low event activity. So this is the probability of making a jet in central compared to the probability of the same scaling in peripheral. So they have split it up into event activity, and then they plot it as a function of X. And you see the suppression and the basically either a slight enhancement due to the NPDF or unity, with the same argumentation as I was just going through with the others at RHIC.
Yeah, so the point is that all the saturation effect are coming from a very small rapidity region then, because it's the initial state effect.
Yes,
And is it possible to ascertain whether in the P-lead or P-gold collisions where you showed these collective effects, is it a initial state effect or it is really hydro-like or QGP-like droplet?
As far as I'm aware, there's no way to reproduce these results. Let me get to it. I have it here somewhere. Sorry, let me just animate my way through. These type of results at either the LHC, that you get this scaling of the V2 within, at the case of RHIC, whether it's PA, PDA, or helium-3A, the splitting of the V2 and the V3, or at the LHC where they manage to go into much more detail to look at the particle ID. They see evidence of radial flow, this bulging, that the heavier particles go to higher transverse momentum. We haven't managed to really be able to do those calculations using non-hydrodynamic type modeling. We took the initial state and take extreme NPDFs and say, well, what if I say cold nuclear matter effects are very extreme, that there is some cold nuclear matter energy loss? You still don't really match the data. They tried with ideas of maybe gluon saturation kicks in early and that's what it is, but they can't match all of the data. You can maybe get one, but then it doesn't work for everything else. The only way we've really managed to explain the wealth of data, I've only shown you a tiny little bit here, is via using sort of hydro type ideas. So it seems very clear that there is hydrodynamical like behavior in the most extreme, not in the average PA collision, in the most extreme average PA collisions. So these are normally the top, like here you see it's the top 5% of the highest multiplicity. So in the very extreme cases.
Thanks, yeah.
Yeah. I cannot see, but I have one question. Helen, as you discussed on this slide that Phoenix, they measured in P gold, V gold, they see V2. But when we measure in star, jet substructure and other measurement, and we don't see any modification of jet. So, I mean, which way we should think on these results if we put all these results on table?
So the picture I have is that indeed you can make a little droplet of Quark-Gluon Plasma, but it's so small and the expansion is so fast that you just don't have time to see the partonic interactions of the high Q squared, that just the energy loss that's there so far. I mean, the precision of our data is good, but it's not that said, it's very small, that there just isn't the time scales and the volume of the QGP are just not sufficient to be able to see this energy loss. So the energy loss, if it's there, is very, very small and just not seeable on the scales that we currently have. And that's part of the reason why people are very excited to be looking into this more, because Nihar, as you well know, but maybe not everybody in the room does, we've now also taken oxygen-oxygen results So we collide oxygen-oxygen, which gives you a very similar number of binary collisions as in these very extreme P-lead type collisions. And in the oxygen-oxygen, we are seeing evidence of jet quenching. We are seeing evidence of final state that can't be explained. There is a jet quenching in the most fully overlapping OO. The jet is suppressed, and even at mid rapidity, it's not just at forward, looking into the P going. You see signs of some evidence of substructure changing. The dijet balance has been shown. The LHC also now have oxygen-oxygen, that we see that the dijet imbalance is there, that the subleading, which passes all the way through the collision region, is suppressed. So we think our picture is becoming somewhat clarified, that you can, unlike we first thought, make a little QGP droplet in small system collisions, not on the average, but on the extreme case. And if you take AA, where we can really better control the geometry of the collision, you can even start to see jet quenching signals. So it's not that it's everything shows you flow light signals and there's never jet quenching in small systems.
Yeah, I agree what you mentioned. And do you think that if we do some measurement at low PT, relatively low PT at low PT jet, for example, then can we see some modification on jet structure or in that direction?
One might be able to, and that would be an interesting study. I mean, of course, as you go to very low jet momentum, it becomes questionable, is it really a jet? And what substructure can you have for a 5 GeV jet? But I think that probably is the question, because indeed that gets us to different regions. Maybe there's time to see some interactions in there. So I think that remains an open question, and it's a very good one. Like, if we can get to more and more detail, change the regions, look in these sort of where there might be, can we ever see an effect of jet quenching? And I guess, Phoenix would tell us that they do see it, right? That we just don't know how to do the normalization properly. I think we do. And I think there is some tension between these results. But, we have to take these seriously. So I think that's a very interesting question for students to be tackling. How do I put the Phoenix data into a clear picture that is consistent with everything else we're seeing?
Yeah, please.
So, hi, Helen, this is Sören. Hi, very nice talk. I mean, I wanted to follow up exactly on this picture of the Phoenix that you showed, right? I mean, one should be, I mean, I guess one should also be able to do something similar at the LHC, right? I mean, I don't know, whatever, using Ranjan to normalize this or something like this. Is this being looked into, or has this been done, or?
I'm not aware of it having been done. I'm sure somebody is looking into it. It's quite a complicated procedure, because yes, that would be great, right? Because the naive arguments sound very reasonable of what Phoenix do, right? Force the photon one to be at unity, it's colorless, it shouldn't be interacting, is an experimental way to get to NCOL, no modeling needed. And then you get what they see. But, I guess, I don't know why the LHC hasn't come back, because these results, I mean, they were only published somewhat recently, but because they were so unexpected, it took quite a lot of discussion in the field. So they've been known about for a while, but I don't know. And it is quite a simplistic explanation because especially, which would be nice for the LHC to do, because that is something for people to muse about, is, as I said, this is a pi zero, not a jet. It's the leading one. So there is some discussion about whether, when the photon ideally gives you the q squared of the actual collision, the partonic interaction, whereas the pi zero being high momentum, and this is high momentum for RHIC, is correlated with the q squared, but there is some smearing out because it's the leading, but it takes 100% of the partonic energy, or maybe only 20. So there's a big smearing. So maybe this is just showing you again some of this, when you take a very extreme pi zero, you're picking again some extreme case of a biased event selection, and that's what does it. So that is part of the discussion and where some faction of the community sits. But I'm not sure it's been conclusively shown. And one would imagine that the LHC, with their higher statistics, their bigger jet energy, could repeat this exercise as you just said, but replacing pi zero with jet.
Yeah. Okay.
And they had photons, right? Or W's and Z's. So, but I'm unaware of anyone having done it. It's a very good idea. One of the students sitting there should be on this, right?
Yeah. Yeah.
Am I audible?
Yeah. Please speak, say your name and.
Hello, am I audible?
Hello, yeah.
It's Dhanush here. Can you please go to the slide number 15?
15.
15. I see that there is a comparison between PT, some PT and other PT. You have done it in the forward region. Can you expect the same result in the mid region also, mid pseudo-rapidity region?
So I believe these are mid-rapidity regions. So it's measured across their whole one. The selection here is on the event activity. So they're trying to look at forward regions to, again, try and measure what the event multiplicity is in a region that's not affected by the fragmentation of the hard scattering. So I think that's why they go to these large eters, is to get away from where the jet fragmentation might be. So you're truly measuring the underlying event multiplicity, not, well, I have a jet, so I have a lot of particles. Did that answer your question?
Oh, yes.
Because if I did this event activity at mid-rapidity where the jet is, because the jets are high energy, especially at the LHC, lots of particles would just correlate with high energy jets. And that's not what we want to do. That would be like a self-correlation.
Yeah. Okay. Thank you, Helen, for joining. And I hope you will have a very good day tomorrow. Otherwise, it will be too much stressful for you then.
Thank you. Good night.
Thank you.